I'm Tony Firenzi with PCWA, but I'm not alone, and I'm not the most qualified speaker on this topic, which I think qualifies me to get through the overview of it the quickest. But we have some greater expertise in the room. Why don't you guys just say who you are and maybe look into the screen? I think it can kind of see you.
Yeah. Darin, Reintjes, I think everyone knows.
Yeah.
And Brian Rickards with PCWA.
So thank you. And now I'm going to go into PowerPoint mode. So yeah, we're here to talk about our basin study, our climate change analysis that we did with the Bureau of Reclamation. Just to check in, somebody speak up if what you're not looking at is the front slide of a PowerPoint. And I'm just going to go into a little bit of an overview of what basin studies are and a little bit of a recap. I know Brian and Darin have both presented at the plenary and a fish meeting on this study. It was before we had all of our results out, and we're starting to get to a point where we have results. So I'm just going to do a slight recap on what you had seen before. It's going to be very brief. And that starts with, what is a basin study? These are studies sort of co-led between the Bureau of Reclamation. It's done under their Water Smart program, and they go look for local project sponsors. And they found this group that you see here, and I think it's worth naming them: PCWA, City of Folsom, City of Sacramento, City of Roseville, El Dorado County Water Agency, and last but not least is our sort of leader, and the one that brings us all together is RWA. So those are all the local project sponsors on this thing. Basin studies, again, are sort of invented by the Bureau of Reclamation to analyze climate change in a watershed, identify water supply and demand imbalances, and then identify ways to adapt to that. That's essentially the whole point of a basin study. I think they've done 14 of them in the Western United States, and about half of those have been done in California. We'll get into a little bit of the uniquenesses of our basin study as we move along, but I think it's probably worth saying at this point, one of the uniquenesses is the more, excuse me, the level of detail that we got into in the modeling. We did take it a good step further than most basin studies that are out there. And lastly, before I move on into the presentation, is a couple of limitations. First is I'd like to talk a little bit about the granularity of the information that we arrive at through this basin study. It is a high-level study. It's meant to identify water and supply and demand imbalances. And so it doesn't get into the granularity of stream hydraulics and sediment issues or hourly time steps and that kind of thing. They leave that for further study. So that's important to understand. Another thing is where these basin studies come from. This is probably the third time I'm saying the point of them is to analyze under climate change conditions, water supply and demand conditions, and identify imbalances. So it's sort of an analysis or an effort driven by the idea or the objective of water supply. It doesn't mean that we don't look at other matters like environmental impacts of climate change and what have you, but the focus is imbalances in water supply and demand. And then lastly, the availability of information. Right now, the study is in a draft or like an administrative draft report, and it's not out for public consumption. We have some information in this presentation that sort of brings some of that to light, and that's fine. But unfortunately, we can't follow up this presentation by sending everybody those draft reports. So eventually they will be made available, but they're just not available at this time. And so with that, I think I'm going to move ahead. I have about 30 slides. My thought was I tailored the slides. We were given questions, a series of questions about a week ago. And I looked at those questions, and we all put a considerable effort into choosing slides that address those questions. And so my thought was, at a brisk pace, move through these 30 slides, just to show you the information that we've provided for this group. And then reserve the rest of the time, which would give us more than an hour. As Tanya had said, dialogue is better than presentation. I'd like to get to that dialogue. And so what I'd like to do is then either pull the questions up or whatever Tanya recommends at that point, but create the real meaty portion of this gathering, going over those questions. But a flyover of this presentation would provide a nice backdrop for that. I should probably do a check-in. Tanya, is that okay with you to take that approach?
Yeah, sounds good, Tony.
Thank you. Okay. The first 3 slides, many of you or all of you have seen before. This is just the study area. It's the American River Basin, plus the North American subbasin or groundwater subbasin and the South American groundwater subbasin. And so when you add all that together, you get that polygon there. That's our study area. Next slide. This is just from before. This is what we told you were anticipated outcomes of a basin study. And again, it's modeling tools for projecting water supply and demand imbalances. So that's what we had last told you we were after in a basin study. And what we left you with next steps was to, we had done a lot of the modeling, but we haven't digested the results. So we spent the last 6 months digesting those results and formulating adaptation portfolios. The whole, the intended outcome is long-term strategies for dealing with those imbalances. And again, that is a high-level objective. And then when I spoke earlier about this study having a relatively coarse level of granularity of information, it's because we're looking for strategies, not real specific outcomes. So that's it. That was the recap. Now I'm moving on to new information. And so here's the rest of the presentation. More on modeling. A lot of the questions that were asked had to do with, by the way, very good questions, very technical questions. So I'm sorry, but the presentation does get a little technical because I think that's what you wanted. And so we'll go into the modeling, high-level results. I have sort of rebranded the adaptations, which is a bureau term, to supershed. And there's lots of reasons for that, but the RWA region is kind of trying to take a holistic view at water management, and that's being branded as the supershed. And again, 5 goes to the Q&A, and that's where we want to spend most of our time. So more on modeling. This first few slides, they're not actually model results. This is data that we've observed. And I thought it was just a nice backdrop or a nice context to show what we've seen as far as climate change thus far. This is temperature data at Blue Canyon along Interstate 80. It's up in the foothills or the Sierras above Auburn, where our office is. And this goes back from the mid-century to now, and we've seen about 3 degrees of warming through, it looks like, about 2017 or 2018. So just a little bit of historical context of what kind of warming have we seen thus far. And then we're not just interested in average annual temperatures, which is what you just saw, but what about the cold weather that has to do with snowpack? And so what this chart is number of days in any given year where we had freezing temperatures. And you can see a pretty substantial decline in those real cold winter days. And so again, that goes from mid-century to recently. This is a chart of runoff through our watershed. And if you look at total water year runoff and you do a trend line, and Darin, I think you're the one that did this trend line, right? It's you see a slight drop in that trend line, but not a major one. This is, again, total annual runoff. But let's take a look at spring runoff. This is April through July, which basically is historically relied on snow melt to produce that runoff. And when you plot the same or a trend line through that, you see a much steeper decline in the trend. And by the way, that is actually more than 100 years of data. That doesn't go back to the mid-century. That goes back to the early 1900s. That's it on historical data, but just to provide a little context. Now I'm really getting into the modeling. This first chart is just to, or this first slide on modeling is just to talk about climate models. These are global models that we're talking about. So I think people always want to simplify things, and they think of modeling as, oh, you did a climate change model in your watershed. That's not really how it goes. These are models of the entire globe and then we go and take the results and adapt them into our watershed. And so around the globe, there's listed here under, I guess I should go ahead and read out the acronym. It's Coupled Model Intercomparison Project. It's a global project where experts around the globe have got together and put together data sets to provide sort of a broad range of analysis tools and data for doing sort of climate change analysis. As of this slide here, and I think this number does change a little bit over time, but there were 61 global climate models and 4 emission scenarios that were analyzed. And so I'm going to start with the emission scenarios. Here's the 4 right here. And I'm going to use my cursor. It's going to move a little slow. I should ask, do you see my cursor? Maybe I'll look to Tanya to answer that question. Do you see my cursor? And it's okay if you don't.
Yeah, I'm not, usually we can see a cursor, but I'm not seeing it.
Oh, yeah, we're having a video. Okay, that's okay. I just need to know that I don't get to use a pointer. That's fine. So I'm looking at the lower right chart, and that is carbon dioxide emission. And just because I think people understand what carbon dioxide is better than some of these others. But these global climate models look at lots of constituents that lead to climate change. And the one in the lower right happens to be carbon dioxide. And it's real, there's some sort of adopted emission scenarios that have been generated. And they're called RCPs, or Resource Concentration Pathways. And they're numbered. I'm not an expert on them, but they have numbers 2.6 up through 8.5. And so those are sort of globally accepted scenarios of emissions to look at. And sometimes when people talk about climate change, you'll hear them talk about economies and, you know, a fast or an aggressive economy versus a slow economy. And what they're talking about there is not, you know, how's your local housing market or, you know, business or that kind of thing. What they're talking about is industrialization and world consumption of fuels. And so 8.5 represents what people often term as business as usual, and you can see a relatively exponential growth. And then another one I would just like to draw attention to is RCP 4.5, which is in the middle there, and it's a little bit more tempered. It's business as usual in the early days, but then some of our more proactive things we're doing to mitigate climate change start to take effect. And down at the bottom, only on the lower right, you see something called commitment. And my hunch is that is the international accord on commitment for climate change that I don't believe any countries are actually in compliance with. I'm not quite sure. I'm not an expert on climate change, but that is the sort of the what everyone brought together as a lofty goal. So those are the 4 scenarios available for analysis. And so now I'm going to get into how did we bring these results, this global scale model, down to the American River. So it's not Scripps University, but it's a Scripps Institute, I believe, came up with a methodology to take those 60+ global climate models and do what's called a downscaling routine, where they take the results, and just to illustrate it, you see a typical global climate model scale. And those are real granularity scales that you see there on California. And sort of downscale those results to something much more refined on the right. And just for context, the global models are about a 90-mile square, 90 miles each direction. And the downscaled results are something a little bit less than 4 miles in each square. So you can see you get to a much more refined analysis. So what Scripps has done has taken 32 of those 60+ global models and downscaled them, and they've done it for 2 emission scenarios, RCP 4.5 and 8, was it 4.5? Yeah, and 8.5. And so that creates 64 downscaled models, again, global, that we can use, but then you can take those results and bring them into your watershed. And so I want to talk a little about what that looks like. So I'll try to do this pretty quick because it is quite technical. But what you see there on the right is a chart of 64 dots. Those are the average conditions of climate change of both precipitation, which is on the vertical axis, and temperature, which is on the horizontal axis. So if you take the outcome, the average outcome of those 64 models for those two parameters and just scatter it, that's what you get. They need to find a way to narrow things down for the kind of analysis we want to do. And so they came up with a statistical method which goes 10% each way of the center. And those are those dashed line intersections that you see. And the polygons there, basically what the polygons do is identify the 6 closest models to that 10% point. And they do that for a lower quadrant, lower left quadrant, which is wetter, drier. No, I'm sorry, warmer, drier. And the upper left quadrant, which is warmer, wetter. Upper right quadrant, which is hotter and wetter. And then the lower right quadrant, which is hotter, drier. And then there's a central tendency. And so that what this does is it creates 5 scenarios, but there's actually 6 models for each scenario. And then they have to go through a relatively sophisticated statistical analysis to generate model results that are sort of averaged over those 6 models for each of those scenarios. So it's rather elaborate process. Yes.
Hi, Tony. There's a question about what is on the horizontal axis. What is on the horizontal axis?
Okay, yeah. The horizontal axis is change in temperature. And so it goes from 0 up to just over 6 degrees Celsius change in temperature. Okay? And I'm happy to answer questions like that. And I do want everyone to know that as we get into answering the specific questions submitted to us, we intend to pull back to these slides as well. But also, don't let me go by without answering those questions.
That's great. So Tony, yeah, because make sure that folks, that you raise your hand and you put a question in the chat box if there's something that you don't understand, because then of course that creates a foundation for us to continue the presentation. So could you go, that question was related to the previous slide about what was on the horizontal axis.
Right here?
Yeah.
Oh, elevation.
Okay.
And so, yeah, that is just elevation.
All right. Thank you for clarifying.
Mm-hmm. Of course. Okay. Sorry, I digressed a bit, or was getting a little too detailed there.
And then we just have a few more questions. So actually, can we go back 2 slides? Another one, another one. Okay. This is the slide that we were talking about. Right, Barbara, is this the one that we're referring to? Where you wanted to, you had a question?
Yeah, I assume it's time, but I don't know what scale of time.
Oh, thank you. And what was your name again?
Barbara Evoy?
Okay, Barbara, thank you. I apologize for that. And actually, it's kind of convenient. I meant, as I go through these slides, to point out when there's a slide that I think speaks to one of the questions that was submitted to us, and this is one of them. People had asked, what do emission scenarios look like? And the scale on the horizontal axis is time 2000 through 2100. So it's 100 years. And so each tick mark is 20 years. Did that answer your question?
Yes, thank you.
Yeah, sorry about that. I don't know why the time scale is not on there, but yeah.
Thank you for clarifying. And Clyde, you have a question?
Yeah, question is for the chart that comes next, the scatter diagram, what year is that?
This, Brian, do you know the answer to that? I think it's probably at 2100.
Yeah.
But that's a guess on my part.
I don't recall. I know it's the annual average for the whole entire watershed.
The reason I was speculating 2100, Clyde, is the point of that scatter plot is we don't have one of those scatter plots for every year showing or anything like that. It's only to identify which 5 scenarios, what defines each of the 5 scenarios, and what 6 models will result in those 5 scenarios. And so it would stand to reason that they would go out as far as climate change modeling goes, which is to year 2100. But I don't know that for a fact. And I'm not sure. I'm looking around.
That
the room.
seems reasonable.
Yeah.
Yeah.
And Clyde, if that's, we can any questions you have that we can't answer, we can get answers to. Okay?
Fine.
Thank you.
Thank you so much.
Okay, so that is climate modeling, and then the American River Basin Study wanted to ultimately use CalSim 3 to analyze water supply and demand conditions, but we have to get from the climate modeling to runoff conditions to get there. And so we have this modeling called variable infiltration capacity, or a lot of people call it VIC modeling. And it's a hydrologic model that takes the inputs of climate change of temperature and precipitation, along with the soil conditions and everything else about our watershed that is inputs to the model on a 2-dimensional grid, and it outputs runoff conditions which ultimately yield watershed runoff. And that watershed runoff then becomes inputs into CalSim. So VIC is a transition model to get from climate modeling to CalSim. So that's VIC. And then talk a little bit about CalSim, or CalSim 3. So I'm quite certain most people in this audience know a lot more than I do about CalSim. I think Brian might have an answer you were going to look for. Did you find anything?
Yeah, so Clyde, I looked up at the scatter plot, and we developed one for each time period simulation that we looked at. So we developed one for 2050, 2070, and 2085.
And we probably don't know which one is on the PowerPoint there, but.
No, I'm not aware of. Sorry.
Don't be sorry, that was good. Okay, and so, yeah, we wanted to use CalSim 3. And CalSim 3, of course, integrates groundwater flow in as a supply into the, or as a storage unit, if you will, into the modeling. But one of the achievements of this basin study was to enhance CalSim 3 with local conditions in our watershed. And I think this is probably as good a time as any to mention, I'd mentioned that there were 14 basin studies done by the Bureau. One of them was the entire Sacramento, San Joaquin, Central Valley basin study. And they used CalSim, but what was a little unsatisfying about that basin study was the way CalSim represented the American River Basin and Folsom Reservoir. It was just not enough detail and not enough granularity. And so one of the achievements of this basin study, which was really just to hone in on a critical area that we see, number one, because we live and work and all that here, but also because of its complexity. The American River Basin is relatively complex. And so you can see we sort of called out changes on the right there. And just a blow up of the level of nodes added to the most of this. I think there were only like 2 nodes or something like that, Brian. I'm recalling it, the original CalSim before we added all of this detail to it.
I think Folsom Reservoir was the upper node.
Folsom,
Yeah. So everything above Folsom Reservoir was added to CalSim 3 as part of this effort.
Hey, Tony, I think I saw an error there on the.
Oh, you did? Yeah.
Yeah. I'll talk to you offline. I think I see.
Yeah. No, I appreciate that, Tom. Yeah, I think I might see the same one you're talking about.
And Tony, we have a question. I think it's back at that cluster diagram again.
You bet.
And Rob, why don't you just ask the question, Rob Burness?
Yeah, I'm just wondering whether the cluster scenario was different, done for different years, to see if the clusters represented this pretty much the same models, or whether the models were very much different in clusters for the different years, say 2100 versus 2050 or the like.
Brian, can you recap what years did we do clusters for?
So we ended up looking at an annual average across a 30-year period for climate change. So what we did is we took the years 2040 to 2069, and we mapped the annual averages for each one of those. So for the 30-year period, we did essentially a graph just like you see on the right-hand side. And we did one for each time period. I think the big reason why we wanted to do that is, again, what Tony mentions, we wanted to select the 6 different climate change scenarios or climate change models.
Mhm.
And we wanted to have the same models depicted and analyzed for every grid, for every month, for that time period.
So Brian, how many of those plots, did we have 30 of those plots then, one for every year?
We had, so 12 plots for every year times 30 years.
Okay.
So,
And so it would be, we probably can't answer off the cuff, what is the variability in that scatter per
correct.
plot. So that's a relatively complex issue to look into, but we could if warranted.
Well, I'm asking simply because I wanted to get a sense of the consistency of the models that were selected for being representing a centralized cluster in different years.
Okay. Yeah.
And I'm not aware. I know this is a pretty consistent approach with the Bureau and a lot of other climate change studies.
This is a very well adopted approach, and it's been done pretty much for every basin study, but that doesn't answer his question. And let us look at that and respond accordingly. Would that be all right with you?
Yeah.
Okay.
Thanks a
Barney,
lot.
I'm free to move on.
Please. Thank you.
Okay, so that was it on modeling. And now we're going to talk a little bit about the results. I believe if you've seen past presentations, you've seen this slide before, and it's just the polygon of our basin, but with a sort of what the heat map in which you can see is the warming. And I think what I'll do is start with the numeric results. So out of the modeling, we ended up doing detailed work on 3 scenarios. And so we didn't analyze all 5 in every step of the way. We ended up narrowing down to 3 scenarios, and they are warm, wet, central tendency, and hot, dry. And the reason is those 3 capture the full spectrum of conditions that we experience. So warm, wet being the sort of the least impactful to water supply conditions, if you will, and hot, dry being the most impactful, and central tendency being obviously in the middle there. And so for the warm wet, the temperature output is on average about 4 degrees of warming, and that's 4 degrees Fahrenheit. You always have to be careful about what units you're talking about, Fahrenheit or Celsius, when you're talking about climate change. 4 degrees Fahrenheit for warm wet, and just over 7 degrees for hot dry. Those are air temperatures. And then on the plot, what you see is a spectrum. That spectrum is not 4 to 7. That spectrum is the central tendency, the 5.6 degree result. And what you see is that down on the valley floor, about 5 degrees of warming. And then up in the mountains, just over 6 degrees of warming. So it's only about a degree. A lot of people look at this map and go, oh my gosh, look at the gradient. It's actually only 1 degree difference. And there's reasons why there's a little bit more warming up in the mountains than the valley floor, but probably not worth talking about too much there. And then in terms of another look at changes in precipitation and temperature, this is sort of a conglomerate output of precip and temperature over all 5 scenarios. And so it captures the 4 to 7 degrees. You can see there in the, you don't see the minimum of 4 because that's the warm wet scenario. But and again, this is in the middle. But in the on average, the temperature change you can see by season is right there and varying from about 5 degrees in the winter up to 7 degrees in the summer. And again, that's not an annual average. That we were looking at annual average in the previous slide. This one we're looking at seasonal. And then precipitation. And there's questions that were submitted to us, and I may end up coming back to this to be more specific on those questions, but questions were asking what happens to precipitation. And if you just look at average annual precipitation, there's really not a lot of variability. But where you see variability is when the precipitation falls. And you can see that in the fall and in the spring, we get a lowering of, and those are percents on the left, not inches, but we get a lowering. And then in the winter, in the summer, and I wouldn't pay much attention to 10 degrees more precipitation in the summertime, but we do get 5% more precipitation in the winter, which is quite significant. And then snowpack. This is, to me, one of the most important slides here, because it leads to a lot of the impacts to water supply that we're talking about with climate change. And so this is probably worth parking at a little bit. And it actually, this slide does respond to some of the questions that were submitted. So let's talk about what we're looking at here. The top chart or table is peak snow water equivalent in the course of a winter. And so it's not the total snowpack accumulation in acre feet through the entire year. What it is at the peak of snowpack, call it March, April, historically we have just over 1 million acre feet of the white stuff up in the mountains, on average. It's just year over year average. In the central tendency analysis, that 1 million acre feet of peak snowpack is reduced to 406,000 acre feet. Wetter, warmer, you see 487, hot, dry, 245. So in summary, climate change would reduce our snowpack accumulation anywhere from 50 to 75% in the American River Basin. So I'm kind of let that settle a bit, because that's a pretty striking result. In terms of there were some questions about how much of our precipitation falls as snow, so we went ahead and had our modelers answer that. Historically, 22% of our precipitation falls as snow. And under climate change conditions, you see that the results are drastically different there. So you're going to see in the next slide that total runoff isn't expected to be reduced that much. It's just that it's expected to become rainfall rather than snow. And that has some obvious implications for those that sort of understand our watershed, which I think most people on this call do. So what does that mean for Folsom Reservoir? I do believe this is a chart you've seen before. And let's focus on that top row there, historical data. And really, it's just a pictorial distribution of runoff into Folsom Reservoir. And you can see that on average, it's 2.58 million acre feet of runoff that enters Folsom Reservoir. And the peak of runoff would historically occur in the early spring. And as a result of the slide that I just showed you, call it I'm going to just sort of talk about end of century. You don't see huge differences between mid-century and end of century. You don't see a huge reduction in total annual runoff, 2.5 million acre feet. There's a slight reduction. And by the way, that slight reduction is due to the fact that rainfall does have greater losses than snowpack. And so there's just a ever so slight reduction in total runoff that occurs because of that. But the real impact is when it occurs, because it's falling as rain, that runoff occurs in the middle of winter instead of the spring, and it happens to be coincident with Folsom Reservoir flood operations, which with undersized reservoirs, at least undersized for these new conditions. I should be careful about what I mean by undersized reservoirs, but it's certainly undersized in terms of capturing that 2.5 million acre feet of runoff. So impacts to Folsom Lake storage. This is, I didn't put the time. This is end of September storage. And with the baseline conditions, the dashed black line up top, and the 3 climate change scenarios that we ran full modeling on from central tendency, hotter, drier, wetter, warmer in 2070, down on you see as the other lines there. And what you can see, I kind of wish I had a pointer here, but where you see over in the sort of the critical dry years are shown on the left as what's called 90 and 100% exceedance events. Those are kind of like the events that we experienced recently in the drought. And even that wasn't as bad as what you see here. And those lead to getting close to what you would call a dead pool in the reservoir. And so what this chart illustrates is that under those, at least under the central tendency and hotter, drier scenarios, we could experience about 1 in 7, 1 in 8 years, a dead pool type situation. And again, these are, remember, as I start to show these results, which can be quite alarming, all of these are unmitigated. It's business as usual circumstances. The whole point is to use this modeling to identify impacts and then identify adaptations. And so none of this is illustrated what it looks like if we do an adaptation. And as I said that, I'm pulling up a chart that actually does show some adaptations. It's just a bit of a coincidence. This is river temperatures at Watt Avenue, end of September. And you can see that we have a baseline or existing conditions. That's the black line on the bottom at Watt Avenue. And let's just talk in the middle there. In an average year at 50% exceedance, looks like we're at about 67 degrees or so. And at that same point on an average year, 50% exceedance in the hot, dry scenario, unmitigated, unadapted to the worst case scenario, we would end up with about 7 degrees of warming at end of September. And so 67 degrees could eventually, or it could be 74 degrees. Conditions are worse in drought type years, the exceedance years you would have over on the left, the 10% exceedance and so forth over on your left, and you get upwards of 10 degrees of warming in those kinds of conditions. And then there's a series of lines in between the worst case condition and the existing condition. And those series of lines are the effects of some of the adaptations that we modeled. And so I can come back to this because I know you have questions about water temperatures if needed, unless there's any burning questions right now. And this is the last slide on, I'm almost done, by the way. I'm doing a time check. I probably ought to hurry, and I will. This is just sort of the brass tacks, the skinny on what does it mean for water supply and demand imbalance. And there's a lot of numbers here. I'm going to draw your attention to sort of the bottom line. And I'm going to talk in the worst case right now. So what you should be looking at is the 2070 hot dry column there. And the results are broken into the lower basin, the valley floor, versus the upper basin. And the reason for that is this is CalSim output. And if the way CalSim is just programmed is if there is a supply of water, it will pull it and call it demand met. And because we have a groundwater basin, CalSim in the lower basin draws from that groundwater basin to meet demand. It doesn't mean that we would really use full groundwater supply to meet the outcome of these imbalances, but that's what CalSim did. And so this table shows it that way. So the worst case scenario of 27 hot dry is 155,000 acre feet of added groundwater extraction. I would rather phrase that as 155,000 acre feet of imbalance between supply and demand at the build out conditions of 2070. Some of that could be met by groundwater, but some of it could be met by some of the other adaptations that we've talked about, such as conservation, shifting supplies over to the Sacramento River, groundwater banking, which would provide conjunctive use and that kind of thing. So that's the lower basin. The upper basin, the same scenario, is 87,000 acre feet, and it actually, CalSim shows it as a true imbalance. And the reason is there's not a groundwater basin to draft from, and so CalSim outputs a unmet demand, if you will. So the hot dry scenario is 87,000 acre feet of imbalance in the foothills and upper basin, or in the upper watershed, and 155,000 acre feet in the lower watershed. The warm wet, which is the least impactful scenario, 155 becomes 62, and 87 becomes 63. I think that's enough on that. This also shows how much demand is being met by surface water, how much by groundwater, and that kind of thing. I won't go into any of that now. We can come back to it if needed. That is it on high-level results. I just want to talk a little bit about the adaptation portfolios that we've put together. I'm not going to provide numerical impacts of them. The only place that you saw that was on that temperature chart at Watt Avenue, but there are quantitative results on the effects of these adaptations, but I just felt it was getting a little too deep to go into them. And so there they are. The first thing before we talk about the adaptations is a high-level summary of what we saw as our vulnerabilities. And the first one is that Folsom Reservoir is small. It's not quite 1 million acre feet for a watershed that produces something north of 2.5 million acre feet, which is okay when you have 1 million acre feet of snowpack. And so you could argue that you have 2 million acre feet of storage. But when you lose 50 to 75% of that snowpack reservoir, creates a vulnerability. And Folsom Reservoir is simply not big enough to mitigate that. And that kind of parlays into that second box there, reliance on snowpack. We have obvious risks in wildfire and water quality impacts as a result of that. We've already sort of been suffering some of that and are dealing with it. There is a reliance on surface water supplies, the sort of the supplies that you see particularly CVP and issues with Big Delta and competition for surface water that goes on statewide. And
not on the list.
Was that a question or somebody just?
Oh, could you please go on mute?
Thank you. Okay. And then groundwater management. What I would like to say to wrap up is the vulnerability between surface water and groundwater is that right now our uses of groundwater and surface water are a bit siloed between each other. We've done a lot for conjunctive use in the last 20 years in this region, but there's still a lot more we could do. And we still have a lot of agencies that are solely on groundwater versus solely on surface water. And if we started integrating those agencies a little bit more, breaking down some of those water supply silos, if you will, it creates a water management opportunity that is a key adaptation that we're talking about. In terms of, I'm just going to blitz through adaptations. The first one is sort of water management and institutional things like conservation, executing our Central Valley Project our long-term contracts, which we just did, and forest management and a few things like that. They're just more institutional, how we are sort of working between our well, I pretty well summarized it there. The next, now we're getting more into project-specific adaptations. There was a reservoir looked at called Alder Creek, a Sacramento River diversion, which has long been in the Waterform Agreement, and it is something that we're pursuing. A federally recognized groundwater bank, Folsom Dam raise combined with groundwater banking. Those were sort of mixed together. We can go into that if needed. Modified flow management standard, and I think that is actually it. So that all comes together as something that we are calling the supershed. The whole idea I heard somebody the other day say that we need to stop thinking about our water systems in a way that separates the watershed from where the demand occurs. You need to have holistic thinking. And the whole point of the supershed is to bring the entire watershed together in terms of proactive management, stewardship of our environment, and sort of reliability for our water supply needs and so forth. And that's why we kind of branded that the supershed. And with that, I'll open it up for sort of Q&A. What I thought I would do, Tanya, or I could do, I'm not sure who has seen the questions, but I could pull the Word file up on the computer and we could just go through them. And if needed, I could go back to the PowerPoint. Or if you'd rather, we could just read questions out loud or what have you. So I'm going to ask you your advice on that, Tanya. What do you think we should do?
Thanks, Tony. I think it would be good to have the document available, but let's not go there yet because I'd like to first see if any of the participants have particular questions related to your presentation. And
Yeah.
we'll probably want to have that handy, right? They may want to go to a particular slide.
Of course.
Does that sound good?
Absolutely. Yeah.
Okay, fantastic. So please go ahead and raise your hand if you have a question. I see a couple hands up already. Chris Brown, go ahead.
Yeah, hi, thanks for the presentation. About 2/3 through, maybe about halfway through, you had a slide in which you showed the change in the snowmelt time and the impacts on runoff. And all three of the lines used the central tendency. And yet throughout the rest of the presentation, you showed us the hot, dry year. I'm curious, that's the one right there with the blue band in the middle, yep, and the three different colored lines. Do you have a slide like this for the hot, dry scenario?
I don't know, Brian. Do we? This was more illustrative.
Yeah, Chris, I think I know we have the data available. I don't know if we have a slide. If memory serves me correct. I believe the worst case hot dry, that 35 days earlier changes to I think 40 or 45.
Okay, it'd be nice to see that data. Thanks.
Okay. Because it relates, the bubble chart is so intuitive. And so I could appreciate you wanting to see that, and we'll see if we can get it. Brian, could I ask that you write down, so we have a couple of data requests. One is the scatter plots.
Yeah, I have a running list right now.
Thank you.
Yep.
Okay, awesome. But I do want to just point out, if just to a relative magnitude of what happens between the warm wet versus hot dry and central tendency. This is it's again, it's a little bit more technical of a curve, but that is one way to see the relative difference. What are the other questions?
Yes, Paul Helker.
Hey, thanks. Good presentation, you guys. And my question was actually exactly on this slide. I think I was looking for your presentation that you made at the workshops in October, because I had sent you a question about the slide that you showed of end of September storage, but I couldn't find that original slide, and my email doesn't include the emails from back then. But it looks like you made some revisions to this projection here, especially for the central tendency, because as I recalled, I think it looked like it was even lower than this. So did you, after that October presentation, did you guys go back and make some changes to this projection?
It is different. Yeah.
Yes.
And I think there was, I hate to say it, I think there were some errors in the analysis of that chart that made it drastically worse conditions than what you see here. Is that right, guys?
Yeah, that early presentation was just that. It was kind of, that was like the first of the results coming out. And so we were shown at that time very preliminary results. And so I think that slide that you're referring to, Paul, did have some problems with it and has since been revised. And so I think I believe this is the latest.
Yeah, it is.
Yeah.
Great. Yeah, the previous one was pretty scary looking. It was about half of this.
It was, so this shows dead pool about 1 in 7, 1 in 8 years, and it had dead pool about 1 in 3 years.
Under the hot dry.
Under the hot dry.
Okay, thank you. Paul, any follow-up there? Just you go ahead and lower your hand if you don't have any follow-up, Paul Helker. And Ron, I see your hand up, Ron Stork.
Remind me what reclamation still has to do and what it intends to do with this study, and what is its non-federal sponsor intend to use this for, and is there a difference of opinion between reclamation and PCWA on what needs to get done to, quote, finish this study?
I'm going to start it, but Brian, if we need to go into more detail, would be could do that for you. First, though, I'd like to clarify, PCWA has no, we were the project manager on it for the non-federal sponsors, and actually for reclamation. They used us as a project manager. But in every other way, we are just an equal in this effort. And so all of us participating as non-federal sponsors, those shown on the first slide, would be able to, would have that opinion. So we're not going to, take authority to steer that kind of thing or what have you. In terms of what needs to be done, there is a draft report that has been circulated to the sponsors, both to reclamation staff and to the non-federal sponsors to just review and comment on. Some comments have been made, and they're incorporating that. There's some little tidbits of technical work that still need to be done. And the plan is to have a public sort of rollout with presentations where we would share in final results near the end of this year. And it's anticipated that after, and I don't know if it's the regional director or who at the reclamation, is it somebody in Denver, has to sign it.
Correct.
And then it's certified and done. I don't think there is any disagreement between locals and feds on that aspect. And in terms of what are we going to do with it, remember early on in the presentation, we said this was intended to identify imbalances and identify strategies to work or to manage with those imbalances, manage water supply and everything else with those imbalances. And those strategies need further development, further technical work, feasibility studies, and that kind of thing. This is a very high-level programmatic document. And so what I would say we intend to do with it, and I'm going to offer it up to these guys to kind of say their thoughts on it, but would be to sort of look through those strategies, and if any of them look like feasible alternatives, then start to analyze them in greater detail. And actually, at some level, some effort has already begun on that. We recently got a federal grant to analyze the Sacramento River diversion project in greater detail. And we also received a federal grant to analyze the water bank in greater detail. Do you guys want to contribute anything more to that?
I think Brian, correct me if I'm wrong, but one other process that's currently under being taken right now is the technical sufficiency review. And so I don't know if that's been completed, but I think the results of that will also be incorporated into refining the final draft.
Darin, you're right. They finalized that. I think they got the last comment maybe last week or so, the last reviewer. So they're in the process of sifting through those. They had a lot of great comments. I think it was 100 plus. Some of them were large, some of them are minor grammatical things and whatnot, but they're in the process of sifting through those before they go up higher up in reclamation to get the regional directors and higher ups approval.
Thank you. We have a couple questions. One in the chat on Barbara Evoy on slide 24. Where does the imbalance in groundwater come from? Is it realistic? Is the infrastructure already there to supply the groundwater, or is this another needed project if others don't add capacity? And Barbara, did you want to add anything to that or clarify before they respond?
Well, I realize it's just a plug-in, but especially in the upper basin in the foothills where there isn't much groundwater, it seems like we're talking significant infrastructure up there, and water banking may not overlay the foothill demand area. So I was just curious whether it was just a plug-in, whether someone had thought further about what that actually means, or whether it's just simply a number stuck in.
So you're talking about specifically for the hot dry scenario, 87,000 acre feet of imbalance. And
yeah, well, especially where we're talking, in the foothills where there isn't a groundwater basin essentially, and you're going to need 87 or 63 or 76. You have other projects sort of scoped out that might address perhaps the water banking in the lower basin, but then some other storage. But I just wondered how realistic it was as a plug-in number for the imbalance.
Sure. Your question, at some level, it leads to more questions, and it's difficult to answer because really having to do with the granularity of the analysis we've done, which is just looking at wholly all the water suppliers, all of their customers, and all of our water supplies put together. There is a separation between the foothills and the lower basin, but that doesn't mean that if we were able to adapt to some of the unmet demand in the lower basin, that could actually have benefit to the foothill areas. I'm not sure. I think I would need to understand. I'd probably have to analyze closer where these imbalances are specifically occurring to see, do they result in the need for infrastructure, if you will, to move water from one place to another, that kind of thing. I think we might need to have you repeat the question a little bit to help answer it. But I would like to say, again, it's a misnomer to think that the lower basin, that the result of the imbalance is just that we go to pure groundwater pumping. Our adaptation portfolios, including the water bank, are not that. They don't look at just pumping groundwater as a means to make up for the imbalance that you see there. So I wouldn't say that the situation in the foothills is all that different than the situation in the valley floor. The whole of our water systems needs adaptation to remedy that imbalance. But I don't know. Do you guys want to take a stab at it? Because I'm not sure I completely understand.
I'll take a stab at it. I mean, I don't think we're intending to really pump more in the foothills in the future, right? So in there, it says the demand met by groundwater in the foothill just continues to be a stagnant 1,000 acre feet in the foothills. But in the valley floor, we do take a little bit more of a stab, like you said, and it's not necessarily that we are going to pump, but this is also in 2070 adaptations, right? So, I mean, we are analyzing adaptations that are going to mitigate that and dip into that 155.
Mm-hmm.
So we are analyzing it, and the intent for this basin study is not necessarily to minimize that gap or solve this gap deficiency. Is to analyze certain portfolios and themes that might act well and model well for our supershed, for our watershed. Is that answer?
Yeah, Barbara, we should probably let you repeat if we're not satisfying your question.
Yeah, no, thanks. And it wasn't a well thought out question, obviously, because I'm having trouble articulating it. So it just seems that a lot of your solutions are the projects you've identified need to line up well with the source of the demand and where the gaps are. And I just, that overlay that you threw out real quickly, those projects at the very end. And so I just wanted to see from the Sigma perspective whether or not the projects were lining up with where the demand was. As you know, pumping uphill is a problem. And so I just wanted to see what the thinking was on where that that imbalance was occurring and what the source of the water could be to meet that.
Yeah. Okay. Yeah. And it is true that I went through the portfolios very fast. I felt like I needed to sort of wrap it up, but also because I don't have with me numerical results on the performance of those different projects. There are some numerical results. They haven't really been, what I would say is digested and put into a form that even for us, even the draft report we were given doesn't quite have enough information about those. And so we've asked for more information about the quantitative output on each of the adaptations. So there's even information that we are still yet to see that we need. And I think most important is to understand that these adaptations should be thought of as strategies. And each of those strategies needs its own feasibility study to identify things. And groundwater banking is probably the easiest to understand. It's easy to think about groundwater banking across the entire basin, like we can just take, have puts and takes in the groundwater or between groundwater and surface water all over the place. But ultimately that requires pipelines and connections between water suppliers and that kind of thing to ultimately work. We haven't fully detailed all of that, certainly in the basin study. Now there is ongoing work on the water bank that maybe they've done some more detail on that, but that wasn't made part of the basin study.
Thanks.
Okay, thank you, Barbara. We have a few hands that are up. Rob Vaness. Does someone want to get in there? I heard a voice. Rob?
I'm interested, I'm struck by the fact that there were 61 or so models that were started out as being within the scope of this. And by the fact that over the last dozen or so years, the pace of change in climate change impacts and melting glaciers and all of that has increased dramatically. So that the modeling I'm struck is something that is changing, and I'm wondering to what extent this basin study process that you've laid out lends itself to being updated every X number of years and to reflect continued increase in knowledge, understanding, and data about the pace of change related to climate impacts.
That's a pretty insightful question,
Yeah.
Rob. Thank you. I think it's important to realize the climate modeling, again, is global scale modeling. Scripps Institute has made available 64 scenarios, if you will. They've taken 32 of the models and run them under 2 emission scenarios to generate 64 what they call downscaled results. The frequency of them updating that is not something I'm privy to. I wish I was, but I'm not. But what I can tell you is the effort involved in going from those 64 scenarios to the hydrology and runoff modeling that we did, that VIC modeling I talked about, and then to go from that to CalSim is a huge undertaking, requiring many different consultants and agencies. The climate model, or the downscaled result analysis, and the VIC modeling was done at the Technical Services Center of the Bureau of Reclamation in Denver. Those are people that is what they do. They're experts on it. And then the CalSim modeling was done by a consultant working for the federal government. And so what I would say is, as a water manager, I think your question is very good. In other words, we need adaptive management. We don't really know which of these climate change scenarios is actually going to occur. But we can see the climate change happening in real time. I mean, we're seeing evidence of that all over the place, right? And so adaptive management would say that we need to periodically check in on what what are the conditions that are prevailing? And what does that mean for the assumptions we've made that have led to our water management proposals and projects and everything else? And I'm not sure that revising the climate modeling it's something we may want to do, but I wouldn't say that it should be done all the time. What I think we have is we have results for different scenarios from from really bad to not as bad. All of it's bad. And I think those outputs are probably good enough for water management decision-making moving forward. But where we could do a little bit more of what you might describe as real-time modeling would be on the CalSim side, particularly with different project proposals and things like that. That's not to say that maybe a decade from now, we say, well, it's time to re-up and find out what's happened in the sophistication of climate modeling and redo the whole thing. But I just wanted to illustrate the level of effort and complexity involved. So I hope that was a satisfactory answer. I'm happy to elaborate on it or hear from these guys if we want to go into a little bit more on that.
Rob, did you have a follow-up?
No, I don't think so.
Okay, thank you. You can go ahead and lower your hand. And I'm going to go to the chat, and then I see Chris, Brown, and Ron. You both have your hands up. I'll get to you in just a moment.
Sonia, can I do a check-in on something?
Yes, of course.
I just want to make sure, I'm sort of new to this team and everything, but we were given a list of questions. And I do believe this conversation is answering those questions, but for those that wrote and submitted those questions, are they feeling satisfied? I just want to make sure that, those questions are being addressed by this conversation. So
yeah, yes, good, very good question. And I was about to go to Ted, and Ted is one of the primary writers of those questions. And we could also check in with Clyde about that. So Ted, I'm just gonna, Ted, are you able to, you've been having some technical difficulty. Are you able to participate via Zoom? If not, I could read your question, but Ted, are you there? Okay.
Can you hear me?
Yes, I can.
Can you hear me?
Yes.
Yes, I can see the presentation, but every time I try to actively participate, I get cut off. So might be just as easy for you to read it.
Okay, I'll go ahead and read it. Okay. So
or I can summarize it. Basically, I'll just summarize it very quickly. And again, thank you very much for the presentation. I have learned a lot. And I think your response to Rob was at part have. I'd like you to turn to the last portion of the climate change questions that deal with the model. And there are several there that are focusing on the concern about a worst case analysis, since the use of the model and the various scenarios tend to gravitate to a central tendency. And one concern might be that if we have not accounted for worst case drought conditions, will we underestimate what these conditions might be moving forward? So I'd like you to comment on that, and also if you could on the guidance that's coming out from DWR, came out from DWR in 2018, that's tending to direct those responsible for putting together GSPs to come up with a climate change assessment using different tools, and whether this, in your view, is the superior tool, or whether you have a comment on that.
Okay. I'm actually going to take the last question first because it happens to be here in front of me. And so for others in the audience, they can see it there. And then we'll talk about the question on, extreme droughts and things like that. So it is true, DWR for GSPs has guidance on how to analyze climate change in those studies. And the same is true for urban water management planning. I think I'll talk about them a little bit separately. So DWR, what they're expecting is Pretty much every groundwater sustainability plan out there is going to have done some hydrodynamic groundwater modeling as part of their groundwater sustainability plan. And that hydrodynamic modeling leads to water budgets for the basins. And what DWR has provided for in their guidance for GSPs is it's extremely high level, and it basically says that that groundwater sustainability plans need to account for climate change impacts in developing and analyzing those budgets that come from the hydrodynamic modeling. It doesn't say how, but DWR is offering data sets of what climate change impacts are. And what those data sets can be used for is to post-process model outputs of those budgets. So almost like percent reductions based on changes in precipitation and evapotranspiration. And those changes and those conditions can be used to take groundwater model output and modify it post-process to generate sort of quasi-climate change results. That is sort of a canned DWR option that many groundwater sustainability plans will probably use. I believe DWR allows in their guidance for you to use more local analysis, more sophisticated analysis if available or if desired. And I would tell you that what we've done here is certainly, from a standpoint of sophistication, higher than what minimal guidance is provided or minimal options are provided for DWR and the groundwater sustainability plans. That's not to say, and I don't believe our region has already decided how to analyze climate change and our up and coming groundwater sustainability plans for our basins that are within this analysis. I know you have a conversation about groundwater coming up, and I think that probably would be a better conversation then. But there's probably some technical decisions that need to be made on what's best for our groundwater sustainability plan. But what I can tell you is, if you just go with the bare minimum analysis provided by DWR, it would not be true climate change modeling, and it would not be as sophisticated as what we've done here. For urban water management plans, it's even more coarse. And truthfully, they haven't even issued the guidance yet. The law requires that you account for climate change in your urban water planning. DWR is working on their urban water management plan guidelines. I believe they're supposed to be done at the end of this year. Doesn't that make about sense? Usually they're getting them done at the end of the year, and then we have 6 months to write the plan, right, Brian?
Yeah, I think they're shooting for July or August, like soon.
Oh, good. Oh,
to do a draft guideline.
Oh, draft guideline. And okay, and then in normal DWR fashion, then it's all wrapped up at the end of the year, and you have 6 months to incorporate it. But I am quite certain that what's going to come out of urban water management plan requirements is not modeling. It's probably post-process analysis of your results, or probably even less coarse, or probably even more coarse than that. So what we've done here that I've described in this presentation is more sophisticated than either of those options. That's not to say this is the only or the most sophisticated way to model climate change in a basin. There are other ways to do it, but this is the most common one, at least in the Western United States. Did that answer your question on different sort of guidelines for climate analysis?
Yes, it does. Thank you.
Yeah, no problem.
So the second part of my question is, you partially answered in talking with Rob, but it really is just sort of, will this model provide enough perspective of worst case climate assessment, climate impact, such that the plans that you're proposing would be sufficient to adapt for that kind of situation?
Okay, Darin wants it.
Hey, Ted. And I think this also addresses Rob's question. Can you go back to the RCP charts, the representative? So the two representative concentration pathways that were incorporated into the study were the 8.5 and I think 4.5. So the 8.5 is obviously our worst case scenario in this study, and you can see on those charts the 8.5 is considerably worse than others on the metrics, and so from that sense, I think we're saying we're capturing the worst case. But even in the climate change science community, there's already debates over whether that 8.5, because the 8.5 is the do nothing approach to no actions, basically.
Insignificant industrialization in
Right.
countries that currently don't use as much oil, right?
Exactly. And so there's already debates about whether that 8.5 is even relevant anymore. There's a lot of debate that says that 8.5 is actually too aggressive. So there's that side of it, and I would say that I still think it warrants us looking at that scenario, kind of having it as a bookend, as a worst case scenario. So I would say that we have covered what we would consider right now the worst case modeling scenario. So those hot dry scenarios that we're looking at, those are most likely mostly these RCP 8.5s. And so when you look at the results of those, I would just take it, just consider that being worst case scenarios, and even in the climate change community, thinking maybe that's even too aggressive. So I think we have captured that worst case scenario.
Thank you.
Yeah.
Thank you.
I would just throw out, if you want to see a lot of technocrat commentary, go look at a technical debate on these RCPs and which ones are appropriate.
Yeah, that's right.
You will be loaded with entertainment.
Yeah.
Okay, Chris, your hand is up. Chris Brown. Chris, you're on mute.
Yeah, sorry about that.
That's fine.
Took me a moment. Yeah, well, just one brief comment. Really, I had two questions. One is an extension of Ted's question, which is, does the model at all provide any insight into the length or depth of critical periods? Or is it all just annual numbers?
Oh, well, they are, these are monthly time steps, by the way. That's a fabulous question, Chris.
I'll try to answer this. So, Chris, for the most part, we're looking at historical data from 1915 to 2015. Mm-hmm. So that is our perceived historical data set that we apply these future climate change perturbations to. That's just a data set that we're applying these perturbations for. Now, we can apply these perturbations to any type of data set. So, example, we can apply it to a 5-year drought period. We can apply it to a, extreme water year. It's just at this point, it's almost impossible to summarize this in a report. So we're choosing to apply it to annual averages. We've chosen to model certain events for dry periods. But end of the day, we have a common data tool, a model that has that flexibility.
In moving forward with the planning process, just to follow on, will you look at those questions of the length of the critical period and the depth of it, et cetera?
If there's evidence that we should, Tanya, were you trying to chime in there?
No.
Oh, okay. I'm sorry. I thought I heard something. If there's evidence, so let me give you an example. I saw a question in here about using, tree ring analysis to look at, maybe historic, prehistoric mega droughts, that kind of thing. And is that some, we only have 100 years in the rearview mirror here. And is that enough? I think isn't that fundamentally the concern? And that is a very good concern, by the way. I used to work in flood control, and I remember trying to analyze what the 100-year event was in the Sacramento region back in the late 90s there, and I felt like about every time we redid the modeling, we had a new 100-year event because we had new data. So yeah, our rear view mirror doesn't go back real deep. There is a task for the Technical Services Center in Denver to take a qualitative look at tree ring data and sort of provide commentary on what that means in comparison to our look at 100 years worth of data. If that qualitative commentary says we're missing something, I think it would be incumbent upon us to do some analysis on that. But I can't comment on that right now because I just haven't seen anything that says, here's something you need to be considering. But as good water managers, we certainly wouldn't want to put our heads in the sand on information that might come to us.
Okay, and then the other question, I won't, other people have other questions, but, and I could go on like this with you for a while, but
Well,
in your,
we'll run out and grab a couple of cold drinks and keep going. It's Friday evening. Yeah.
That's right. We can have happy hour here on Zoom. But in terms of your slide 24, it's showing demand being met by wet water supplies. And I'm curious if you've looked at demand being met by demand management.
Yes. I probably don't need to go to it to answer the question, but I will. What was 24? Oh, 24. There we go. Yeah, thank you. Oh, my mouse, get there. Okay. So what you see in this table is the imbalance created by business as usual water management combined with climate change, okay? You don't see anything in here in terms of adaptation. So we end up with 155,000 acre foot imbalance in the worst case if we do nothing and we do business as usual. One of the adaptations is conservation. And so we actually have quantitative results of the benefits of conservation. Excuse me, my phone's ringing here. We have quantitative results of what conservation does to chip away at that 155,000 acre feet, okay? And so what you see here is a non-adapted output. Did that answer that?
I'm interested in those results too. More beers on more Zoom calls.
I would agree, and that you are seeing sort of the latest and greatest in terms of output. Our consultants owe us more information, more granular information. Of course, they wrote the report in a way where it just says, and all these projects did great stuff. Well, we want to know how great, you know, and so we'll see more on that.
Okay.
And we certainly will have public presentations on that output.
Okay, thank you. Clyde, go ahead. Chris, you can go ahead and lower your hand. Clyde? Clyde, you're walking around and you're on mute.
And Brian, did I do enough on that, or I mean, do you?
Oh, Clyde, we can't hear you. You're on mute. And so while you're getting off mute, there's something in the chat. Someone in the chat asked if they could get access to the questions that the environmental caucus developed.
And I don't think that's the meeting answer, right? That would be probably for somebody else to answer.
Yes, and Clyde, since you're one of the primary authors of that, I wonder what your thoughts are about that question.
Sure, I think it's totally fine.
For us to just.
I don't think there's anything secret about it.
Yeah, to circulate the questions. So,
yeah.
So we'll make sure that we do those for those who are interested. Thank you, Clyde. But your hand was up, so go ahead.
Yeah, I was wondering if we're having more rainfall occurring in the wintertime, does the model that you guys have gone through take into account
how much additional water goes out as flood releases?
The CalSim test, right?
The additional water, though, I'm sure there's a way to quantify it.
Yeah.
I'm just wondering if that's actually.
In other words, let's make sure we sharpen the question here a little bit. So we have more precipitation occurring in the winter, and not only occurring in the winter, but occurring as rain rather than snow. Reservoirs are full. There's only so much demand on our water supplies in the middle of winter. So naturally, some of that water then continues on down the river and out into the ocean or what have you. And are you asking, did we quantify that? Like what that sort of lost opportunity is?
Well, you show we've got about 1 million acre feet of snow right now.
Mm-hmm.
And as you look forward, you're going to have significantly less. And some of that water is going to come down the river at flood time. And it's going to go through Folsom because it has to be released for flood control. So that's going to be a loss of part of our precipitation. And the question is, did the model take those kind? I mean, you may not have the granularity to do this. Maybe maybe you're working on a monthly step instead of a daily step, or floods almost an hourly step.
I'm gonna bluntly answer that question because I'm confident in it, even though I'm not a CalSim modeler. But I was part of the dialogue that Brian sort of led in providing the information you see in front of you. And the answer is yes. CalSim is a sort of merger of hydrologic routing and water supply, and it's on a monthly time step, and it uses or it accounts for that that flow through the system. So it absolutely captures the fact that instead of being stored as snow, or instead of being stored in a reservoir, that water is flowing through the system in the middle of winter. It absolutely captures that.
Yeah. Okay, thank you.
Mm-hmm.
Thanks, Clyde. Well, I don't see any other hands or questions in the chat box, and we are right on time. Well done, everyone. We're just a few minutes over. But before, Clyde, I'll just lower your hand. I think you don't have a follow-up question.
Alan, they just raised their hand.
Alan, did you have a question?
Yeah,
go ahead.
First, thanks for a very good and informative presentation. I'm interested in the implications towards soil erosion and sediment yields and how that might impact reservoir capacities. Has anybody been looking at how erosion and sediment might be elevated based on this CalSim 3 output?
Yeah, Alan, that's it's a good question because that is a real consequence of climate change. Unfortunately, it gets to a level of type of modeling, sophistication, granularity of modeling that is, I wouldn't say beyond the scope of this study, but like way beyond it. It's almost a completely different type of modeling. It's sediment transport modeling and hydraulic modeling in our rivers and even on hill slopes. That kind of modeling exists, and it would be an equal amount of effort to all the modeling we just did to then go and do that kind of modeling. That's not to say it's not needed. I'm not sure it's needed for the scope of what we were looking for here, which is supply and demand imbalances. I'm an old sediment transport modeler, and so I do have an appreciation for it. But it's I would say anecdotally, we have seen sediment buildup in our reservoirs in PCWA's watershed. The King Fire was devastating and exposed soil and baked soil. and sort of devastated tree cover in a manner that has resulted in very significant soil loss into or off of the hillsides and into our reservoirs. So, I mean, we're sort of living and breathing the results of that. But in terms of modeling, I would say it's just a type of modeling that is beyond the scope of a basin study.
This is Ron Stark. I could probably add to that. The reclamation a number of years ago reassessed the capacity at Folsom from 1,010,000 acre feet to 975. And at least in conversations with reclamation, they thought that half of that was more sophisticated bathymetry, and the other half was sediment transport, including the Folsom, the Auburn cofferdam washing into the reservoir.
Oh yeah.
So, so at least we have some sense of let's call it 17,000 acre feet of natural and unnatural sediment transport into Folsom Reservoir during its life. Say it started in 55. I don't have a good clue what sediment transport has been into the PCWA and Upper American River reservoirs. They tend to be in fairly sediment poor granitic basins, but you know, in some areas they've got some soil that can erode, particularly after fires. But we'd have to check in with PCWA and SMUD on what they believe has happened historically. And then but Alan's question is, well, what do you think is going to happen in the future? And it is helpful to look at history, but it's also helpful, I think, to look at the vulnerabilities of the hillsides washing into the river channels and then having sediment transport at least until they get into the block. Remember that the North Fork actually has a debris dam whose only purpose is that, and as far as I know, still has a fair amount of water volume left, and it's inflow equals outflow project, so it doesn't factor into the active storage in the basin. It's just a debris dam built to allow the resumption of hydraulic gold mining in the Sierra, of all amazing things. Fortunately, that didn't happen. So at least the North Fork, and not the Middle Fork, has got some sediment blocks. And the South Fork has some significant sediment blocks, and those are relatively small reservoirs with not a lot of storage, and therefore aren't really part of the hydrologic modeling for water yield. They're electricity production facilities, but they do block sediment transport in the South Fork American.
Yeah, we have something similar in the Middle Fork project, Ralston Afterbay,
Right.
Which has captured over the years lots of sediment. I can't speak to acre feet and that kind of thing off the top of my head. What I can tell you is that as a result of King Fire, that number has grown substantially, and to a point where it's triggered us to have to do more work to get rid of the sediment. So at some level, the combination of those sediment blocks, you know, Ralston Afterbay, Clementine, and the one you mentioned on the South Fork, it helps sort of first line of defense for Folsom Reservoir. That's not to say no sediment transport gets into Folsom Reservoir, but those reservoirs help. But then that means, for instance, we PCWA have to clean out Ralston Afterbay.
You could do that.
Did you ask, do we do it?
Yes.
Yeah.
Yeah, we're After bay and interbay, probably every 5 to 10 years, we're doing sediment removal from those reservoirs. The larger reservoirs are pretty high up in elevation, and they're large reservoirs. We haven't done full bathymetric surveys on those. They're not, they don't impact operational capacity or anything like that. So it hasn't really been a concern at this point. I know there are some of the universities are taking kind of a closer look at these and modeling, and so it's being considered and looked at. We don't have any actual data on the upper reservoirs, but yeah, I mean, Tony's right. Ralston kind of is that block in the Middle Fork. It does collect, and it did collect a lot from the King Fire, and we do have it's part of our maintenance program to remove sediment from time to time.
But Darin, you're putting that sediment on the shoreline downstream of Ralston, are you not?
No, not necessarily. That's different. So that's
for gravel.
That's for gravels within a plan. A lot of the like King Fire material wasn't the right type of material for that, so it is actually removed from the site.
Okay.
So I just want to break in here if I could, because we are 10 minutes or so, less than 15 minutes before the hour. And so a couple of things. First, I want to check in with especially the Environmental Caucus and the principal writers of the questions that were submitted to PCWA to ask you if there are any of those questions that you feel you'd like that you'd like responded to now, because we could take 5 minutes to do any follow-up on those questions. And then, of course, we have at the NSC, we'll be able to debrief at our meeting next week. We'll be able to debrief this discussion and identify what other topics related to climate change couldn't be answered in this discussion, and then we'll decide where to go from there. But let's just take a few minutes. Are there any questions that were in that list that you'd like us to address in a few minutes here? Okay, let's talk next steps. We know that we have more these foundational issue briefings coming up. Next week at the regularly scheduled negotiating steering committee meeting, which is on the 16th of July, next Thursday, half of that meeting is going to be dedicated to a fisheries presentation, and the presenter is Chris Hammersmark. And again, there were several questions that were developed by the Environmental Caucus and discussed with the 2x2 group. And for those of you who may not know what that is, the Environmental Caucus chose 2 representatives, and the Water and Public Caucus chose 2 representatives that had been working together to prepare for these foundational issue presentations. So thanks to all of you for your work on that. And that's Paul Schubert, Jim Pfeiffer, Clyde McDonald, and Ted Rao. And so that group will continue to meet to prepare for these upcoming presentations. So that the fisheries one will occur next week. And then on August 4th, there will be a groundwater and surface water presentation on August 4th, and Rob Swartz is the primary presenter for that presentation. I know Rob is on the call today, and so thank you for participating, as well as Chris Hammersmark. So those presenters are going to try to create as much of a line of continuity as possible in this educational phase. Anything else related to next steps, Tom, that you'd like to chat about?
Thanks, Tanya. I just want to say thanks to the PCWA team and to the other study participants. I know Levi Johnson's on the call. I actually think Reclamation deserves a nod. I think it's pretty outstanding that a federal agency under this administration can be actively moving forward with a serious climate change investigation. So kudos. You know, Tony and Brian and Darin, you guys basically put yourself in the hot seat for an hour and a half, and I think that you guys executed your task really well. Thanks for the, yeah, thank you. Thanks for the grace under fire, and thanks to the Environmental Caucus members. I suspect that Environmental Caucus folks, you're probably going to want to debrief on this at your next meeting, and I'd invite the other caucuses to do the same. If there is need for additional conversation like this one around climate change or around these kind of investigations, you know, our process team wants to make room for that if the desire is there. I guess I also want to point out that I heard that the water managers in this basin are moving forward with basically additional investigations based on this stuff. And I think I'm going to go out on a limb, and I think I sense that members of the Environmental Caucus have a keen interest in those forthcoming studies. And I will even take a guess that they might even want to take part in being part of some of the solutions you might be trying to work towards. So Environmental Caucus reps, feel free to disagree with me if I've gone too far out on that limb. And other than that, just want to say thanks for everybody. Thanks to everybody. Really good session.
Yeah, thank you. And some follow-up items, we will distribute the questions that were requested, that were put together by the Environmental Caucus and discussed at the 2x2 group. And then PCWA, your team there, Tony, Brian, and Darin, I know you've been taking notes about some technical follow-up. And do you want to share what your list is, just so folks can hear?
Yeah, absolutely. So I have 3 questions that I have that have yet to be answered that we'll follow up with the group. But one is, what is the variability of the 6 climate change models over various time periods? And this was one, I don't remember the gentleman or lady that asked this, but I wanted to follow up, and I wasn't sure if this was specific to the 30-year time period, or if
that was Rob Burness.
Okay, or if it was specific to over the 3 time periods looked at, 2050, 2070, and 2085.
It was the 3 different time frames, just to see whether the same models were showing up in the central clusters over the periods that you looked at.
You good? Yep. All right.
Okay.
Next one is, can we see a bubble chart for the various other time periods and climate change periods? So we just looked at the central tendency, but looking at the other bubble charts. And then the last one I have is, what are quantifiable results of the demand management portfolio?
Or I would say all of the portfolios.
All of them?
I mean, yeah, and that may take time, right? Because they got to kind of work on that. But I mean, I shouldn't put words in someone's mouth. But somebody wanted us to.
I think that was Chris, maybe.
Well,
I think that was a general question. How do the conservation, the various reservoirs, the water banks, what percentage of the solution could they offer? Are they in the right places at the right time? You know, how does it all figure in together?
So quantitative benefits to close the gap created with the imbalances.
Right. Are they close? Do we have great capacity, no capacity? What is it?
Perfect.
Okay. Excellent. Those were the 3.
Those are the 3
right,
yeah.
Okay. Excellent. And I do want to get some input from folks, just your pluses and deltas, what you liked about today's meeting and what you would have changed, because that will inform our upcoming presentations. But Rob, I don't want to ignore your hand. And before I go to you, I want to answer Paul's question in the chat. Yes, the recording from this presentation will be available. And so we will download a file and we'll be able to get that to you. Rob.
Yeah, I think this was a very useful discussion to have, and it does illuminate the complexity and the importance of the efforts that are underway. But it also strikes me that the Water Forum members have a potential role to play in providing some policy guidance or overall suggestions for moving forward over time and the use of climate change data effectively in water supply management planning, particularly as it relates to, or as well as it relates to groundwater basin planning that is underway. So I think going forward, it's worth collectively thinking about the kinds of policy statements that we can reach consensus on that would provide that kind of guidance to the regional water system management process.
Excellent. Thank you, Rob. Thank you for bringing that and putting it into context of the Water Forum agreement as well, because that is really what we're doing here in creating that foundation. So thank you, Rob. And I'd like to just open it up to the full group in the last few minutes that we have, the last 3 minutes, to ask you what you liked about this presentation, about today's meeting, how it was formatted, the kind of information that you received, what you would have changed, again, to inform our future presentations in this educational phase. Rob, is your hand still up to give feedback? No. Okay. Any feedback we'd love to hear.
And don't hold back because of us. We have thick skin.
Barbara.
I wasn't going to talk about your thick skin. I was going to compliment you and say, thank you so much for putting it together. There's a lot of information. I don't know, without doing a side-by-side of the questions to the slides, whether or not we got through everything. And I guess that's sort of the proof is in the pudding. At the end, there were a lot of questions that were handed to you. So I can imagine you didn't get through all of them. No, thank you. It was a lot of stuff there. You worked through it well. It was well presented. Clearly, the three of you work well together. And so I just wanted to thank you for spending the time.
Thank you, Barbara.
Thank you. Tanya, I would say that the questions did help guide the presentation. So, I mean, that was, I guess, one comment.
And I would say we probably got through about 2/3 of the questions. So we got like a D. We got a D.
Oh my goodness, thank you.
Well, there might be a curve.
Okay, anyone else? We'd love to hear your comments, your thoughts. Okay, is that all we've got on a Friday afternoon at 3:59? I think so.
Yeah,
all right. It's been a pleasure. Thank you all. We look forward to getting this presentation out to you and doing all the other follow-ups we talked about. And also look forward to seeing you at the future presentations. The next one up is on the 16th at the on fisheries. Okay, thank you all. Have a good weekend.
Thank you, Tanya.
Bye-bye.